Okay, so we've been looking at those power gains and stuff like that. What we want to look today is at absolute measurements. And we hinted at that a little bit the other day. Something called the decibel milliwatt. Yeah, I see that. The decibel milliwatt is basically comparing a power level measurement to an absolute. So the number of dBms is, just as we've been doing, 10 times the log of, it's not power out or power in, just the power over 1 milliwatt, as we saw. So if we measure something and it has a reading of, let's see here. Let's say it has a reading of 18 milliwatts. So the dB level, number of dBms, is going to be 10 log 18 milliwatts over 1 milliwatt. Again, as always, the only reason we're putting in the units here at all is just to make sure they're the same. So then it is 10 times log, oops. I don't even have to put in the divide by 1, I just put in 18. 12.55 dBm. So let's say I have something that is rated at 3 watts. And I measure it and it's actually putting out 3 watts. So its power level in dBms is going to be 10 times the log of. So now that we've got that 3 over 1, though, we realize units aren't the same. So I have to make that 3,000 milliwatts. So the milliwatts cancel out. It is 10 times. What's that? I could have made the milliwatts into 0.001 watts. Yeah, that would have worked. I always like to try to leave the milliwatt as 1 milliwatt because then I don't have to put in a fraction in there. I just put in whatever the top number is. So that's only 34.77 dBm. Well, as we mentioned with our power gain and power loss formulas, measuring power requires voltage and then either current or resistance. Either one of those, current or resistance, the current requires you to interrupt the circuit and insert the meter. The resistance must be done with no power. So either one of those requires you to interrupt service. So it'd be nice if you could measure it just strictly based off of voltage and not have to interrupt service. So the same conversion applies. They created a unit called the decibel millivolt, and that is comparing our signal level to a single millivolt. Now remember, power is related to voltage squared. So your number of dBmV, since it's voltage squared, that squared comes out, makes that a 20 instead of a 10, times the log of your voltage over 1 millivolt. That was voltage squared, but because of the rule of logs, we can take that squared out of there and put it out front. Make the 10 times 2 is 20. So if we have a reading of, let's say, 600 millivolts. So the dBmV is 20 times the log of 600 millivolts over 1 millivolt. $55.56 sounds good to me. dBmV. Why is this useful? Why is it more useful to have it in dBmV than it is just into millivolts? Well, because in dBmV, your gains and losses can just be added and subtracted. For example, let's say you have well, let's just look at going the other way. How many millivolts would a 31 dBmV signal equate to? How many would it be? So it's going to be 31 here equals 20 V over 1 millivolt. Yep. X. You could put X instead of V would be fine. Divide by 20. Okay. Yeah, so you're going to do the, not ln, but 10 to the power, yeah. So that's x over 1, so that's just x. So this is just 10 to the power of 1.55. 35.48 millivolts. Since this is millivolts, if I just drop that, I'm going to make sure my answer's got to be in millivolts is all. Morning. Your test will be sitting right there for you. One of the big advantages of this is, let's say that you have a signal that has to come down and has to go through cable. Your coax cable, which I know is, they're trying to get away from it, but your coaxial cable usually has a loss of, what is it, 9 dB per 100 meters, is that right? 100 feet? Okay. So it's 9 dB loss, so negative 9 dB per 100 meters. So let's say we have an antenna. Pretend that looks like an antenna. And we're going to run from that antenna on the top of a tower we're going to run our cable down to a receiving station. And in this station, we have our box that's going to convert our signal and send it out through whatever. If our signal, let's say the signal coming in here is at 0.9 volts, and between the receiver on the antenna and our box here in the station, we have 140 feet of cable. First of all, we're going to convert this input signal into dBmV. So the input signal, or is the antenna. I probably butchered the spelling on that, but oh well, I did. There. The number of dBmV is going to be 20 times the log. Now 0.9 volts, I'm going to change that to 900 millivolts. 29.54 sounds about right. Ah. $59.08 is what I get to. That is dBmV. And it's labeled dBmV because that's how it's calculated, but it still works like any other decibel. So we've got this 9 decibel loss per 100 feet of cable, and we have 140 feet of cable. So it's a negative 9 per 100 feet. How much is that going to be for 140? Well, we'll cross multiply and divide here. Negative 9 times 140 divided by 100 is going to be what, 12.6? Negative 12.6, I believe. dB. So what that means from this signal here, 59.08 dBmV, we subtract 12.60 dB, and we are going to get 46.48 dB is that signal. That's what's going to reach here after the loss in the cable. So let's convert that. What's that? So let's convert that back into millivolts. Now I'm going to do this in the calculator, so I'm going to take the 46.8, or 46.48, I should say. Have to divide by the 20. And then I've got to take 10 to the power of that. All right, 210.86, 210.9. That is millivolts. So that is the signal that reaches that station. And that really is the easiest way to calculate signal losses. I mean, you could have a much more complex system. You might set up, let's say you've got your rooftop antenna. From there, you're going to run, oh, let's say 40 feet of cable to where you have a box where you're going to split off. And let's say this box is, oh, I don't know, let's say it's a negative 7 dB coming out this port. Negative 6 is very common because you're cutting signals in half. When you have a splitter, usually it's going to be at least a negative 6 because it splits your signal. There's always going to be some sort of transmission loss, insertion loss in that. So then let's say from there we have another 25 feet of cable to a splitter going off for another set. And let's say that that one is a negative, we'll put that negative 5. They do make splitters that don't equally split the signal. So there's one output that's going to be stronger than the others. And actually, even the ones that are supposed to equally split it, one output will always be slightly stronger than the other. And another 35 feet of cable to our main set here. So this is our destination here. Let's see what our signal strength is there if we have 800 millivolts coming in at the antenna here. So again, we're going to start off by converting that into dBmV. So that's going to be 20 times the log of 800 over 1. It's in millivolts, so I don't have to do any conversions. Sounds right. 5806, you are correct. Feels like we just did that one. Okay. So now I'm looking at this system. We don't have to go piece by piece here. Yeah, we've got the negative 7, negative 5, and then we've got our footages. That adds up to, what, 100 feet? So we know that's just going to be a negative 9. So is that 1621? So that takes us down to a 37.06 dB. So then at the set, 37.06 equals 20 log of our voltage over 1 millivolt. So I'm going to take 37.06, divide by 20, then 10 to the power of. You got it. 71.28, 71.29 looks like. Is the signal strength. Let's say that this device here requires a minimum of 100 millivolt signal. with this type of a setup, it's obviously at some point we'll have to install an amplifier. Really doesn't matter where. Generally, it's best to install an amplifier as early in the system as you can. A lot of times they'll install it at the antenna. Otherwise, they'll install it at the first, once it's in out of the weather, the first chance they can get. They'll usually try to do it, most of the time they'll try to do it where there's another device, so you only get one insertion loss. They hook the two of them together. So you're not going cable to amplifier, cable back to next device. Yeah. But anyway, we need 100 millivolts minimum. So let's figure out what decibel level that would be. Well, that should come out to be 40. Which means we currently have this signal strength of 37.06. We need at least to get from 37 to 40, a plus 3 dB amplifier. Now, plus 3 dB, we're doing dBmV, so 6 is doubling. So plus 3 is still a significant chunk. It's about a, I'm trying to remember, plus 3 is like a fourth or something like that, if I remember right. Okay, let's do another system like that. Let's have you try a system like this. We're going to bring in, let's say we're getting 600 millivolts here coming off the antenna. $60 feet. This is going to be an amplifier. Undisclosed amplifier. We're going to have a 6 dB loss here. Another 30 feet of cable. An 8 dB loss here. And another 30 feet of cable to our ending destination here. We need 90 millivolt minimum here. Figure out what that amp has to be. So I'll give you some time to try to figure that out. How's it looking? You want a hand? That sounds a little large. Let's take a look. We could do it either way. We could start here and figure out what we would have with zero amplification, or we can start here and figure out what we're going to require. Let's do figure out what we're going to require here first. So 20 times the log of 90 over 1. 39.08. So require 39.08 dBs of signal here. So now let's figure out what we're getting off the antenna with no amplification, so ignoring this amplifier. Okay, so the 20 times the log of 600 over 1. So that was 55.56 dBmV. We have, from that 55.56, we're going to lose 8, or 6 there and 8 there. 24.8 for the cable. Okay, for the cable, yeah, we've got 60 plus 30 plus 30 is 120 feet. Yeah, we do a proportion. 9 per 100 feet equals X per 120. That is 10.8 when you cross multiply and divide. So we're losing 10.8 dB for that. But yeah, that is 24.8 that we're losing, so that comes out to be 40.76 is where we're at. Does that look right? 30.76, thank you. So with no amplification, where the signal would get through here, it'd be 30.76. We need 39.08. Yep. So what is that? 8.32 dB. So that amplifier has to be probably a plus 9 dB amplifier.
Yeah, I just didn't solve that last part.
Okay. So I mean, you can see that's actually, yeah, there's some steps involved to it, but it's actually pretty simple when you look at figuring out what amplification you need, whether you have adequate signal and stuff like that. I think what I'm going to do is I'm just going to let you go after these and try them. This is in that 21 packet, the new packet. Page 464 to 465. 1 through 10. There'll be at least a couple of questions in there on systems. That old packet went okay going back to it yesterday?
What?
That old packet went okay going back to it yesterday? Okay.